is Dimitri Gurevich, and he will teach us quantum matrix algebras and applications. Dima, you are welcome. And please switch off microphones, except for the speaker.
Йось, я не вижу, сколько слушателей, не видно у меня тут.
12.
Ладно, ну хорошо. Thanks a lot for inviting me to deliver a talk here at your seminar. I will speak about quantum matrix algebras. Finally, it is object related, is the most known, the best known case with quantum groups, but quantum groups is not my topic. Finally, I will present in another way what doesn't mean by quantum matrix algebras. So, что-то я не могу переключить страницу. Ну придется так переключать, ладно.
Сделай Ctrl-L, тогда ты будешь переключать нормальные странички. А так
Ctrl-A делаю.
Да.
Ну, видишь, она цвет поменяла. Ну ладно.
Ну ладно, хорошо, делай как получается.
Вот так вот, поехал, да. Нормально. This is plan of my topic. So now consider the well-known algebra GLN and its enveloping algebra, also well-known. Consider superalgebra GLMN and also its enveloping algebra, also well-known. What's the main difference between these algebras? The algebra GLN is defined as the space and dimorphism of the space V. V is a finite dimensional space as follows. The bracket is defined as follows. We consider two elements of endomorphisms, and we consider the following bracket: x multiplied or times y minus it's necessary to transpose x and y by the usual flipper p. I use the notation p for the usual flipper, and after that we apply the product as well. If we consider super case, GLMN is called superalgebra. The flip is replaced by superflip. I denote with superflip as follows. The only difference. But what is superflip? Superflip is a space, vector space, composed from two subspaces, which are Z2 graded. And transposition of A, B are elements of V0 and V1, is done as follows. And now it's necessary to take into consideration the parity of A and B. So with notation, it's just the parity. Now, now I want to explain how it's possible to represent all elements in the algebra mentioned before in the following matrix form. Let MyJ be the standard basis in the algebra of endomorphism. This algebra is always associative algebra. But now I want to apply the element Mij to element xk, where xk is just a basis in the initial basic space V. Compose the matrix composed from this element Mij and consider the following system. The usual flip P, M1, M2 minus M1, M2P is equal to 0. What is M1, M2? It is a standard notation for the tensor product of the matrix M and identity. Here, identity tensor product M. And also consider the following relation. P, M1, and so on and so on. You see this relation. If you present this relation presented now in the matrix form via entries, the entries, M, Y, G, and so on and so on, you see that the first relation is just nothing but the commutativity of these entries. So it's possible to present this relation in the matrix form or via the entries. It is similar, but this relation means nothing but the entries commute with each other. That's all. Okay. And the second system, where on the right-hand side is something, we have the following relation. I state that this relation say that we have just enveloping algebra of the U, GLN, nothing more. So you see, it is another presentation, but now with the presentation is just via entries. And the previous presentation was just in the matrix form. What I want to say about that it's sometimes much easier to present all relation via the matrix form. And finally, quantum matrix algebra introduced below will be presented also in this form. So I repeat, this system is nothing but relation in this enveloping algebra. And I consider the following example. Now the space V dimension 2 is spanned by X and Y. V squared is 4-dimensional space with the following basis. Now P is a matrix 4 by 4 as follows. It is nothing but the usual flipper. If you put here as a column with vector, you have that with element xy and yx untransposed. That's all. So it is a usual flip. The matrix M, A, B, C, D, M1, it is following matrix, M2 is the following one. So the corresponding homogeneous system with 0 is on the right-hand side, we have the following relation. A, B commute with are commutative, and so on and so on. 6 relation here. The corresponding unhomogeneous system reads, you hear here, AB commute with B, A as follows B, and so on. So it's a relation in the enveloping algebra of GDEq. If we want to get similar presentation, similar matrix writing for superalgebra, it is possible to do in different ways. In order to get supercommutative algebra, we constitute the following system. Here, PMN is supertransposition, M1 as before, and here once more supertransposition, and so on and so on. I state, if you consider the matrix A, B, C, D by block, 4 blocks, finally it means that the matrix A and G are even and B and C are odd. Now, in the corresponding enveloping algebra GLMN, the following matrix presentation. The right-hand side is similar, but here we have some linear terms, because I repeat, here we have all matrices of the same size. So this writing is very good and very useful for writing some relation in the commutative algebra, supercommutative, and the developing algebra, and so on and so on. So another way of constructing supercommutative algebra is as follows, maybe, I don't know for the moment. Here, super flip, supertransposition, here M1, M2, and so on. But what is M2? M2 is M1 transposed to the second position, shifted to the second position via the usual flip P. So it is just notation for M2. It is just, I repeat, M1, and here 2 flips, usual flips. And if we put M2 here, we have here super flip, M1, usual flip, M1, usual flip. And finally, it is not good because we have here a mixture of 2 flip, usual flip P and super flip PMN. For this reason, it is not so good. Finally, the notation, the meaning for blocks A, B, C, D, it is not the same. Below, what we want to do, the super flip will be replaced by some other operators. What operator? I say on the next page. But now I want to introduce in the matrix, in the algebra, commutative algebra or enveloping algebra, the notion of elementary symmetric function. Determinant of the matrix M minus T identity can be developed as follows. You know well. And here we have something looking like minors. Finally, the element which arises here are called elementary symmetric function depending on a matrix M. I repeat that if the matrix M is diagonalizable, so My are eigenvalues of this matrix, it's possible to present with elements as follows. And with elements called power sums, Newton power sums, sometimes one calls with elements, Gelfand elements, but I prefer Newton. Presented via eigenvalues, we have the following form. And you know there are some relation between two families, which is called Newton identity. So it's possible to express, to present one family via the other one. Now I want to deform P and get an operator which is called Braden. I will explain what doesn't mean this term Braden. But now I want to do a deformation of P and deformation of superflip. And finally, I take the following matrix. You see what is difference? Here Q, here minus Q minus 1. So if I put here Q equal to 1, we have here just the previous matrix. Where is previous matrix? Doesn't matter, but you have seen this matrix finally, you get just the usual fit. If we put here Q minus 1, we have here almost the same matrix, but here minus. It isn't. So this matrix is deformation of superflip. So here P as a limit, here P1, 1 as a limit. Now, if we deform the initial system with P and its homogeneous analog by replacing P by with matrix on the previous page, we have the following relation and the following one for unhomogeneous situation. This algebra is called reflection equation algebra. This algebra is called modified reflection equation algebra. So modified means that the right side is not 0. We put here something. If we deform P, instead of P, we write here in the visual, with relation, we have the following one. It is not a good relation between here, because here we have R, which is Braden. I will explain what doesn't mean Braden. And here we have the usual flip. And this mixture is not well. So the question is, what operator are good, in question mark, are good to put in this relation or with one? So now we call an invertible linear operator R acting from V square in the same space Braden if it satisfies the so-called Braden relation as follows. Finally, R1, 2, it is R multiplied in tensor sense by identity, and here similar. But it means, finally, I want to explain what is meaning of this relation. If you take three elements, for example, x, y, z, and you can transpose x and y first, free transposition. Or you begin by transposing y and z. You have free transposition. So two ways are equal to each other. So with this meaning of with-braid relation. Maybe you know that there exists a notion which is called quantum Yang-Baxter equation. It is more or less similar because quantum Yang-Baxter equation is the following one, but it's possible to pass from with writing to with one if we construct a product of with operator at the usual field. If you consider the following operator, so with operator is subject to the quantum Yang-Baxter equation. In Leningrad school, one prefers to deal with Yang-Baxter operator, and maybe this name was given by Leningrad school, by Fadeev school. But I prefer to deal with braid relation. Now, if moreover a Braidian is subject to the following relation, I call it involutive symmetry. If we have instead of with a relation, but Q is not equal plus minus 1, because unless we get just with relation. So now Q is not equal. Q is not equal to 0 as well. So with in this situation, with Braidian is called Heike symmetry, because with a relation is just proposed by Heike. And in particular case coming from quantum group, I will say a couple of words about quantum group a little bit later, but finally the most known quantum group of series A, because SLN is just series A, Dirichlet-Jimba quantum group. It is just an example presented above, matrix 4x4 presented above. Now, I assume Q to be generic. So Q is not with values forbidden for us, and some other means that Q analog of the number K, it is just the notation for Q analog. Q analog of a number is just the following fraction. So it is not 0 for any integer K. We consider general case, but sometimes there exists a separate theory for situation when K is just root of unity. So with quantity is equal to 0. I don't consider this situation. There exists a quantum group of other series, B, C, D, a corresponding operator or matrix, if you prefer, are called Birman-Murakami-Wenzel symmetry, but I will deal only with Heike symmetry. Okay, now, if we have a Heike symmetry, so we consider an analog of symmetric and skew-symmetric algebra. I call them asymmetric and askew-symmetric. So it is the following quotient. It is a free algebra. T on V, it is free tensor algebra. No relations. But after that, I factorize by image of the following operator. Here, similarly, but I factorize by the operator as follows. So you see that we have just here the one factor and here the second factor in this relation. If I put here another difference between I omit here, I cancel here Q, it is not a good algebra. It's necessary to have a good algebra. It means that I want to have this algebra to be deformation of the usual one. It means that it is has the corresponding Poincaré-Hilbert series similar, just the same as the classical case. So this is Poincaré-Hilbert series of symmetric algebra. Here, Poincaré-Hilbert series of skew-symmetric algebra. Here, dimension of homogeneous components. And finally, it is just shown by myself that the following relation, classical relation, if we take R equal to P, so it is just classical case. We have this relation is well known, and I shown this relation in general situation for more or less general Hecke case. And this proposition was shown by this Vietnamese mathematician. So Hilbert series P minus and P plus are the BEF rational functions as follows. So here A, B are positive, but it doesn't matter. What is matter for me, I call the couple R and S, it is just the degree of this polynomial, I call it B rank. With B rank is analog of superdimension. So you see that general situation looks like super situation in this sense. For example, if we consider R coming from the quantum group, here the only M. I don't consider it here a super case. So then P minus is just as follows one. P minus. And you can compute by yourself P plus by using the previous relation. No problem. So if we consider super flip or deformation of super flip, we have the following fraction, rational function. Many years ago, at the end of 80s, I constructed many exotic examples, such that, for example, Hecke symmetry, such that they possess P minus as follows for any n. For example, you can have here 100 and to have the following P minus. In classical situation, here we have always 2, because the degree of polynomials and the number on the second position are equal to each other. But in my exotic example, it is not so. So here, dimension of the space V is n, it is just n, but B rank is 2, 0. 0 because we have no denominator here. So we have only 2 numerator. Okay. So if we have the following case, M0, so no determinator here, R is called even. And I repeat, M in this position is called rank. Now, I consider to each Hecke symmetry, I associate all two quantum matrix algebra. It is just ATT algebra. This algebra is called ATT algebra. ATT, you understand why I use this term, ATT. And if the matrix is subject to the following relation, which is similar to relation presented above, so it's called reflection equation algebra. And if we have on the right side the these terms, it's called modified reflection equation algebra. So they look like the previous algebra, but now instead of the usual flip on super flip, I use here a Hecke symmetry. Maybe it's possible to use here the involutive symmetry as well. And I state that if we have here a deformation of the usual flip, deformation of this algebra is good. It means that homogeneous component of this algebra are classical for general Q. Okay. Below, I will use the following notation. L1 overlined, it is just L1. So overlined or not, it is similar. But if I put here 2 overlined, it is just the matrix L on the first position, but transpose it on the second position, not by P, the usual flip, but with our Hecke symmetry. You see? On the third position, overline it. It is similar. We take L2, overline it, and we transpose to the next position, position 3, by means of the by our Hecke symmetry. And it's, if we use this notation, finally it's possible to present all relation and reflection equation algebra in this form. So this form is similar to RTT1. Here, difference with RTT algebra is that all indices are overlined. In the ordinary RTT algebra, the indices are not overlined. And it's very, very big difference in theory of these two algebra is completely different. Now, similar to the classical case, in reflection equation algebra, I deal mainly with algebra. RTT algebra is not regarded below. So, in reflection equation algebra, it is possible to define an analog of the power sums. You see? But now, instead of the usual trace, I put here an analog of the trace. I could call it quantum or a trace, which is defined by the following formula. It is the usual trace of the matrix M, but multiplied by a special matrix. This matrix, which comes in this formula, is completely defined by initially given Hecke symmetry or involutive symmetry, if you prefer. But how it's possible to construct this matrix, it is not even. Finally, I learned this construction from Lubashenko, who is living in Kiev. Finally, he invited this formula. Finally, it proposed a way to construct an analog of the trace. It's very important to put here a braided analog, or quantum analog, as you wish, of the trace. Always element which are Q analog or quantum analog of power sums, and so on and so on. In the construction below, all construction will be constructed via quantum trace. It's possible also to define analog of elementary symmetric polynomials, and also with a quantum trace. Note that if R is of the rank M0, it means that it is just even symmetry. Symmetric polynomial of the highest rank M, now rank is M, is just quantum determinant. So in this situation, it's possible to introduce analog, quantum analog of determinants, very important property. Because if you put question, what is determinant of a matrix? I will answer, I don't know. I reply, I don't know, because the notion of determinant depends on the setting in which we are working. So the usual determinant are specific for the usual setting. If you reply the usual flip by the super flip or by braiding, the determinant change drastically. Now, Newton identity are valid in new situation. So in reflection equation algebra, as I said, it's possible to define analog of elementary symmetric polynomial of power sums, and as shown in Isaev, Agiyevsky, Pyatov, the following version of Newton identity is valid. But they proved this identity in more general situation, and for the first time it was proven in reflection equation algebra by myself, Pyatov, and Saponov. Also, a version of Cayley-Hamilton identity is valid. You see here, with respect to the usual commutative case, we have here the factor q, q squared, and so on, and so on, and so on. Now, the next chapter, next section. If we have the usual flip, if we put here P, we have a Braden or Young-Baxter operator. It's called in two ways, Braden or Young-Baxter operator, as follows. Well known. It is just a case of Jimbo operator, of Young operator. But I put here A.
What is A in the first formula?
It is an arbitrary number.
Just a number. Okay, thank you.
Arbitrary. So if A is involutive, we compose the following operator depending on two parameters. If A is Hecke, I put here Q in order to stress that A depend on Q now. It's necessary to compose the following operator. You see the difference. Here A is arbitrary, here A is absent, but is U the parameter? Here U is absent. So the statement is, for this operator, we have the Young-Baxter relation, or another way. This operator meets the Young-Baxter equation. Young-Baxter equation is the following one. You see here we have, with respect to the previous Young-Baxter equation, we have here parameters, UV, UW, and so on and so on. Now, why this operator are more interesting? Because now we can construct algebras which are called Youngians as follows way, in the following way. So you put here the operator presented above, here a matrix depending on U, matrix depending on V, and now the matrix depending on U is the following series. So we have here a series, infinite number of matrices, but U is developed in the negative powers. And so with just object algebra introduced by Drinfeld. Drinfeld called this algebra Youngian. And now I want to introduce similar algebra introduced by myself and Pavel Saponov. So we do a similar way. We proceed in the similar way, but here, instead of Young operator, we put operator mentioned above constructed by ours with R involutive or with R Hecke, no, but it is just the same relation. Or maybe a relation as follows. So these generalized Youngians are called generalized Youngians of RTT type, and these generalized Youngians are called braided Youngians or Youngians, generalized Youngian of reflection equation type. And here, as previously, L2 overlined is just the following operator. And with relation can be presented as follows. But you see here R depends on U and V. Here R is constant. Is constant Hecke symmetry or involutive symmetry introduced above. Now, I would like to discuss what is determinant in this situation. Determinant of the matrix L, because of course we have to impose the following requirement. With symmetry R, involutive for Hecke, is even. It means that we have just the Behrens M0, because only in this situation it's possible to introduce determinant. If we have super situation, if we have Mn, what is determinant? It is a difficult question. I don't want to discuss it. So we consider even situation. Determinant of L is given by the following formula, where V and U are two vectors. But you see, In this situation, which comes from involutive R. Involutive R gives rise to rational case. We have here matrix depending on U. After that, shift, additive shift, U minus 1, and so on and so on. And the second case is trigonometrical. Trigonometric, I don't know how it's necessary to say. So here shifts are multiplicative. U is multiplied by something, and so on and so on and so on. So with the difference, shifts here are additive, here multiplicative. And now, what is an L of elementary symmetric polynomials? It is as follows for reflection equation type in trigonometrical case. And what here are operator A. It is skew symmetrizer. Skew symmetrizer maybe, no, I don't present explicit formula, but doesn't matter. Finally, if you take two elements x, y, what is skew symmetrizer? X, y minus yx, and so on and so on. But finally, it's possible to construct an L of skew symmetrizer for any Hecke symmetry and involutive symmetry. We put here skew symmetrizer after product of the matrix L, but shifted, and after we apply a trace on the proper position. And quantum power sums is defined as follows. So you see, in this new situation, U means that we are dealing now with algebra dependent on parameter. In this new situation, it's possible to introduce an L of with symmetric polynomials and with symmetric polynomials as well. And now Newton relation are as follows. So it looks like the previous Newton relation, but now in this relation, parameters come. And so on, and so on, and so on. So namely, I forgotten to say, it's very, very, very important property. All these elements in constant situation, in situation considered above, so without parameters, all these elements, elementary symmetric function, power sums, and so on, is possible to introduce full symmetric function, and so on and so on. All these elements in the reflection equation algebra were central. And now they are not central, but they form a beta subalgebra. They commute with each other. But the only central element is determinant. Determinant is central always, but other elements forms a beta subalgebra. With this reason, why this element arise in integrable system, but in classical situation studied by Leningrad Mathematical School and others. Now, I want to introduce on the reflection equation algebra an L of partial derivative. In order to do that, it's necessary to introduce the notion of quantum double. We have now two algebra, A and B. If we transpose these two algebra, elements A from A and B from B by a map. We call this map permutation map. So if the permutation map is constructed by means of R, we call this double associative double quantum double. So consider the following quantum double. You see, from the first glance, it's very difficult system. Very, very difficult. It is not evident how it's possible to invent that. We invented this system with Pavel Saponov and Pavel Pyatov many years ago. Finally, you see, this algebra is the usual reflection equation algebra. Now the generating matrix is not at n. This is also reflection equation algebra, but R is replaced by R minus 1, but R minus 1 is also Hecke symmetry. And we have the following permutation map. So if we want to permute the matrix D and matrix M, we have to apply the following formula. And finally, I want to say that it is Q-analog constructed by us, which is just analog of Weil-Heisenberg algebra. It is the analog of the commutative algebra. It is analog constructed for partial derivative. It is just analog of transposition of partial derivatives and the initial entries. But all relations are presented in matrix form. And moreover, if R tends to the usual flipper with quantum double, tends to the usual Weil-Heisenberg algebra. So now I want to apply my element partial derivative, new partial derivative, to element M. It's necessary to proceed as follows. We transpose these two elements by usual with map, permutation map. After that, we kill the partial derivative. It means that we put here unity as you wish. And after that, we apply to unity partial derivative. It means that partial derivative disappears. And in classical case, we have the following action. D partial derivative applied to element M is given by the following formula. In general, it is more or less similar. Okay, and now I want to say a couple of words recently discovered by us, Capelli identity. You see, Capelli identity in the classical case. We have a matrix which with commutative entries. We have another matrix with commutative entries, but which are derivative with respect to L, Y, J. And we compose the following matrix. Here the matrix with initial entries, and here the matrix with partial derivative. And I state that if we consider L subject to reflection equation algebra and D subject to this relation, the second relation here, we have this matrix which is satisfied, which is subject modified reflection equation algebra. Finally, it is similar to the classical situation. And classical situation said, if we consider the matrix L, which is constituted from entries, commutative entries, and this matrix is constituted from partial derivative. And if we consider the following product of two matrices, we have matrix which generates the enveloping algebra. It is just generalization of our Q situation. What is Capelli identity? Capelli identity says that some determinant of this matrix is product of determinant of this matrix and determinant of this one. So this theorem looks like determinant of product of two matrices is product of determinants. Nothing more. But here is one problem. The problem is the following. What is determinant of the matrix L hat of this matrix? Because this matrix is composed from non-commutative entries. Determinant is not well defined if we consider is well defined if we consider commutative entries, but it is not so. It is not evident what's determinant. And here I use notation for R data. It is so-called row determinant. I don't want to introduce this notion, so it's necessary in the product of all element in with determinant. What is determinant? Sum of some products. In each product, we put on the first position element from the first row, on the second position from the second row, and so on and so on. So this determinant is called row determinant, and they exist also determinant which is called column determinant. Yeah, it is similar idea, but I don't want to go in detail. And now row determinant here is not determinant of this matrix, but this matrix plus k. And k is shifter. So we add the following diagonal matrix to L, and it is just classical Cayley relation, identity. Finally, it's possible to present the determinant which is located on the left-hand side as follows. It is just classical relation. If we put this relation here, it is another presentation of left side, hand side. And finally, it is just in this presentation, this relation was given in the article by Akunkov. And now our theorem. The following relation holds in the reflection equation algebra. You see, here we have some Q and L of number, and here we have determinant of L, determinant of D, but determinant are a little bit different, and so on and so on. So now I want to mention paper by some Japanese, published in this year. So after appearing the theory of quantum group by Leningrad, finally by Drinfeld, many people came to a theory to study, to look for some generalization, Q and L, quantum and L, of well-known classical result. And so this was the first publication on Capelli identity in Q set. But in their approach, their Q relation was constructed on the RTT algebra, and only in one case related to standard R coming from quantum group. And our Capelli identity is valid not only for standard case, but for all mentioned Hecke symmetries. Moreover, Akunkov in this year introduced the notion of quantum immanent. So you know the notion of determinant. There exists a notion of permanent. Permanent, it is looks like determinant, but without minus. In permanent, only the sum are employed. And the most general notation is just immanent. And Akunkov introduced these notations in the case related to the classical case without Q. And we can introduce Q and L on this object. But an L of Akunkov theorem is only for the moment demonstrated, proven for this case, for Capelli identity. But Akunkov demonstrated more general relation valid for quantum immanent. Finally, it is just our aim for the moment. Now, I want to, so I have to discuss a little bit about representation theory, and so after that, reduction of details follow. It will be the end of my communication. So, you know, if we consider the universal algebra of GLN, representation theory of this algebra is well known, and finally, it is labeled by lambda, partition of any integer k. So we take a partition. It means that the sum of all number is just k, and to lambda we can associate a representation which is irreducible at finite dimension. It is well known. Now, if we want to construct with representations, it's necessary first to construct a idempotent with an L of skew symmetrizer belonging to group algebra of the symmetric group. And after that, we consider the following subspace of V in power k. We apply this idempotent P lambda associated with lambda on the previous page we consider with such space. And finally, it is just a reducible representation of the enveloping algebra. By the sure lemma, the image of any central elements of this algebra, belonging to this algebra, a scalar operator, it's well known. And finally, the problem, how it's possible to compute the eigenvalues of central elements, for example, of Newton elements, or Guilfand elements, if you wish, in this space. This eigenvalues was calculated by Perelomov and Popov. I would like to say that a month ago I spoken to wife of Perelomov. To Perelomov, it's difficult to speak by telephone because his hearing is very bad. But 2 months ago, he had 89 years, his anniversary. Now, I want to replace enveloping algebra by our modified reflection equation algebra. And the theory of representation theory for a generic Q is more or less similar, because it's possible to deform idempotent belonging to group algebra of symmetric group by idempotent belonging to Hecke algebra, and after that it's possible to consider the following subspaces, and finally they are irreducible models over this algebra. So the theory is just similar. And Casimir operator, which I introduced by the following elements, also became scalar. But myself and Pavel Saponov computed eigenvalues of this operator for small k and l. And in general, we have conjectured the eigenvalues of this operator, but it is not so easy to prove with conjecture. Difficult to do. But by using our technique, it's possible to introduce Q and L of so-called cut-adjoint operator, which are modification of Casimir operator. I spoken about this cut-adjoint operator is Sasha Vinogradov conference, but I don't want to speak about that just now. I want only to mention that cut-adjoint operator are intensively used in Gurevich or Gurevich-Kontsevich theory. And now the last section of my communication is reduction a la Drinfeld-Sokolov. So what is classical setting of this reduction? So there exists a Frobenius theorem which says that for any numerical matrix M, by the following transformation, where G is a matrix, numerical matrix, of course, it's possible to reduce any given matrix M to the following form, which is called second canonical form. You see, here we have 1, 1, 1 here over the diagonal, and here only the last row is non-zero. It is clear, it is not difficult to see that the element here are just trace, and so on and so on, and the last is determinant. But now the most interesting case is if we consider connection operator. So we have a similar matrix, but now dependent on a parameter u, here derivation over u, and we assume that this matrix is good, smoothly dependent on a parameter, and according to famous Drinfeld-Sokolov theorem, it's possible to reduce this connection operator to the following operator by the central transformation. We multiply on G depending on U, of course, here, and inverse matrix here. And finally, the Drinfeld-Sokolov theorem says that it's possible to reduce initial connection operator to with 1. And M canonical is just similar with 1. It is just the main theorem, very, very important theorem in integrable Fourier system, because the Poisson structure on reducted space, it is just second Gelfand-Dicke structure. But after that, it is natural to put the question: what is Q analog of this construction of second Gelfand-Dicke structure? What is analog coming from quantum groups? And Frenkel, Reshetikhin, and Semenov-Penshansky suggested to replace operator D by the following one. It is not derivation now. It is just with operator, I don't know what is name of this operator. But instead of the usual gauge transformations, we consider the following one. Here G dependent on Q, U, and here only U inverse. And in this situation, a similar claim is valid. So it's possible to reduce initial operator in more or less canonical form. But what we do with Pavel Saponov? We do with generating matrix, any generating matrix of our algebra, of, for example, enveloping algebra, or algebra, reflection equation algebra, or modified reflection algebra, any algebra where an analog of Cayley-Hamilton identity exists. So I begin here by with algebra, enveloping algebra of GLM. They exist a characteristic polynomial. So they exist some coefficient belonging to this algebra, such that if we put here the matrix M, which generate with algebra, here we have 0. This polynomial is called characteristic polynomial. And they exist a matrix, canonical form, is similar canonical form, units here, and some elements here, such that they exist a matrix C, non-trivial matrix C, that the initial matrix M belonging, which is generated matrix on enveloping algebra, and this matrix are similar in the following sense. Cm is equal to M canonical C. This theorem was proven by Talalayev and Chervov. And finally, myself and Pavel Saponov proved the following, that it's possible to generalize the previous result to any algebra where Cayley-Hamilton relation is valid. For example, this algebra, reflection equation algebra, modified or not, generalized Young of reflection equation type. For example, consider just generalized Young of reflection equation type. Consider the following operator. L dependent on U, it is just generated matrix of generalized Young of reflection equation type. And here, with a derivation is the usual derivation in U. And introduce the following matrix. L canonical depending on U, it is just the following matrix. So where elements here are just concrete elements given by this formula. And our statement claim is they exist non-trivial matrix C such that the following holds. You see, it looks like the previous formula. And this proposition can be shown also by methods which belongs to Chervov. Now, I want to mention some remarks. So what is quantum groups introduced by Drinfeld in the middle 80s? The simplest is just the following one. I mentioned already with quantum group. It is generated by free generator, subject to the following relation. You see that only this relation is in U. But the point is that this algebra, in spite of the fact that it is called quantum groups, it is isomorph with the usual enveloping algebra. It is just the usual enveloping algebra, but presented in new basis, nothing more. But co-algebraic structure, delta means that it looks like a Leibniz rule. So co-algebraic structure is deformed. So as a result, we have another theory, representation theory. If we have two representation, it is necessary to use new coproduct to construct a product or representation and obtain a new representation. So coproduct is deformed. And our reflection algebra is a deformation indeed of symmetric algebra, SLN. I've forgotten here, GLN. And it's possible to say that our modified reflection algebra is two-parameter deformation of this symmetric algebra, the usual symmetric algebra of GLN. And finally, by summarizing up, it's possible to say that if we deform this algebra, which is commutative algebra, and finally we pass to our modified reflection equation algebra, we have as a result a quantization of Poisson pencil. Poisson pencil generated by two Poisson brackets. One bracket is the usual linear bracket corresponding to the SLN Lie bracket, and another bracket corresponds to deformation from the usual commutative algebra to reflection equation algebra. It is quadratic algebra. The point is that these two brackets, Poisson brackets, are compatible. It means that any linear combination of this bracket is a Poisson bracket as well. Finally, what is the difference between Drinfeld approach and ours? He introduced R to T algebra. Before Drinfeld, it was done by Leningrad. By Drinfeld formalized all this stuff. Finally, quantum group is a dual Hopf algebra, so equipped with product, coproduct. It is just dual algebra, Hopf algebra, dual to RTT algebra. And our reflection equation algebra, a modified reflection algebra, can be constructed without any quantum group. We don't need quantum group to introduce reflection equation algebra. We only need Hecke symmetry or involutive symmetry. That's all. And finally, our approach is good for any such stuff. I finished. Many thanks for your attention.
Дим, спасибо. Thank you very much. Questions, remarks, comments?
Зоран, давай спрашивай.
Нет вопросов.
Okay. Well, I better speak English because not everyone understands Russian here. Okay, then thank you very much again. Hopefully we shall meet in the
Слушай, посмотри, сколько народу досидело до конца, я не вижу.
Ну, сейчас 13, но было 15 постоянно, просто уже люди отключились.
Ну, видишь, я, так сказать, в общем, постарался сделать обзор, то есть как бы куда это можно пришивать.
Ага, очень хорошо, спасибо. Thank you very much. So, in a week, we shall hopefully have a continuation of Volodya Rubtsov talk. Everyone is invited, and have a nice week, and see you later. Goodbye.
Bye. Have a nice day.
Ну ладно, ну счастливо вам, всего хорошего.